This video is on recursion, and it's going to be the last video of this course. I do, before we get to recursion, want to talk about pointers, which was in the last video. And there've been some comments from students that pointers seem pointless, that it's just a fancy, complicated way of doing things. So to that, I would say that for what we've done so far, that's a valid criticism. That what we're doing with pointers could easily be done just with regular variables. But we're building the foundation at the end of this course for the next course, which is data structures. So in data structures, it turns out that pointers are essential for us to be able to create memory efficient data structures. And the same is true of recursion. And we'll talk a little bit about the reasons we're going to use it later. If you hear weird noises in the background, I'm pretty close to East Tennessee State University, and apparently they're testing their emergency system, so there's weird stuff going on. But I'm just going to continue on. So let's talk about recursion. The basic idea here is that we're going to solve a problem. One of the ways that we can solve it is by breaking it into a smaller problem, okay, and then solving that problem. We break it into steps, take it step by step. That's a good problem-solving technique. So the example that we always use with recursion is taking the factorial of a number. And I assume that you've gotten that somewhere along the way in a math course, but basically we use the exclamation point to denote factorial, and we have the following definition, that 0 factorial we just define to be 1, and that for any other n factorial is equal to n times n minus 1 times n minus 2, all the way until we get to 0, which is a 1, and multiplicatively doesn't matter, okay? So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, okay? One thing I will tell you as a warning is that factorials get really big really quick. So when you're testing your program, I would keep it to single digits for the most part. So that's the basic definition that we could follow. So if we wanted to solve this in an iterative fashion, or sorry, a recursive fashion, a non-iterative, a recursive fashion, then we could define this recursive definition, and that's one where we reduce the problem like we just said we were going to do, but we do it by calling the function again, okay, on a subset of the problem. So in this case, we have our 0 factorial is equal to 1 as before. But now if we get an n factorial, okay, we're going to define that as n times n minus 1 and call that function again, as long as n is greater than 0, okay? So basically, if we were doing the 5 factorial, we would define it as 5 times 4 factorial. So that can lead to some quicker, more efficient code. No, wrong. Quicker, but not more efficient. It's the efficiency we have to talk about. So when we're doing a recursive definition or a recursive function, it's important that there are two parts. The first part is the base case. So the base case is saying, are we done yet? If we don't have a base case, or we don't have the right base case, we're going to have infinite recursion. It's going to keep going on and on and on, keep calling itself forever. So of the two things that we need, the base case has to return an actual value, has to be able to get the answer. So for the case of factorials, when we get to 0, the factorial of 0 we know is 1. It's not defined on anything else. So we're done. So that's the base case. The other is the recursive case. The recursive case is we have to have a way mathematically to reduce the problem and call the function again. So as we did before, in this case, we're going to take, why can I not use my cursor? There we go. We're going to take n, and if we're sending n to the factorial function, we're going to return n times factorial of n minus 1, okay? So you may ask the question, it's a valid question. We're going to look at a photo from the book here, or a chart from the book here. So what happens when we call the function again? So if you think about the program, we've talked in the last one on pointers that when you go to run your program, the operating system is going to give you a block of memory to deal with. When you then run the main function, the int main, it's going to give a block of memory, that part of the whole program memory. It'll give a portion of it to int main. And then when you run any function, the function is going to get its own portion of memory where it can create variables, do whatever it wants. And then when it closes, that memory becomes available again. So it's the same thing with recursion, except we build a stack of these function calls of the same function. So if we're at the 5 factorial when we send that to the function, so int main is running at some point in memory. The first version of factorial with 5 would be above that. Then it's going to say that's equal, it's going to return 5 times 4 factorial. That stops, opens up another version of factorial, okay, which is going to return 4 times 3 factorial all the way up until we get to 0. When it's 0, we turn a 1. Only then can 1 factorial have an answer, which then flows down to the 2 factorial, the 3 factorial, the 4 factorial, and finally we have our answer to 5 factorial. So I kind of think of this, I like to think of this as you build up like a house of cards, and then they all come collapsing back down, okay? So it's important when we're looking at this idea of factorial to understand a little bit better. We can do most things through an iterative process. Remember, iteration, we've talked about, that's a for loop or a while loop or whatever. So I'm going to use a for loop in this case. It's not true of all things. Some things, and when we get into data structures, we can't do everything with an iterative process, which is why we have recursion. So in this case, I'm going to call this function fact_i for iterative factorial. Okay. It takes an int called num, and I'm going to create what I'm going to store the answer in as an integer called fact, or the factorial, equal to 1. I'm then going to calculate what it's supposed to be. I can use 1 because when I multiply by it, it's not going to change its value. So I'm then I'm checking here to see if the number is greater than or equal to 0. If not, it's not a valid, you can't do a factorial of a negative number. Okay, it's not defined. So we're not gonna be able to deal with that in this case, I'm just returning a negative 99. We usually use that as our guide. Something went wrong. The factorial of a number is never negative 99. It's never negative at all. Okay. So inside of this if is where it actually works. So we're going to say here, our for loop is for I starting at equal to num. So if we're doing 5 factorial, it starts here at 5. It's going to go as long as the I is greater than 0. It's then going to do an I minus minus. So this will do 5, 4, 3, 2, 1. In this case, we don't have to go all the way to 0 because 0 factorial is 1. 1 factorial is also 1. So we can save ourselves a step doing that. At each step along the way, we're just going to take the factorial and multiply it by its last value times the new I. So that'll be 5 the first time, times 4, times 3, times 2, times 1. At 1, it will stop. When it comes to 0, it stops, and we're done. It will return the factorial and print it out. Okay. So if we were to compile this, this should give us a baseline answer, and we can do this in our heads if we think about it. That 5 factorial should be 120. It's 5 times 4, which is 20. 4, so 20 times 3 is 60. 60 times 2 is 120. Okay. So we do get 120. So we're correct there. So let's think about how we would do the function for the recursive function. So again, and down here, I'm just calling it and putting it out in int main. So if I'm going to do a function int factorial r, it's again going to take an int num. Okay. So what I'm going to do here, I'm going to test to see this. I'm going to say, and I'm not going to worry about testing whether or not it's equal to 0 or not. We can do that as well, but I'm going to kind of keep it a little later this time. I'm looking for my base case. Okay, so if num is equal to 0, that was our base case. Okay, so when num equals 0, we know we're done. Okay, we're done, and we return a 1. Okay, else. So again, this is our base case. Return 1. Else, we're at our recursive case, and we're going to return num times, call factorial function again with num minus 1. Not a 2, that'd be a 1. Okay, that should close everything out. Okay, so again, if we call it with 5, it's going to come through, and we've got our int main running in memory. When we hit this line, I have to change this one to an R. When we hit this line in our int main, remember the int main is the first thing that runs when you run a C++ program that you've compiled. It's going to hit this line, it stops. Int main freezes, opens up an instance of the factorial function with 5 as num. Okay, it's going to check to see is num equal to 0. It's not. So it's going to go here. It's going to save this. It's going to return eventually 5 times factorial 4. It opens up a new process. This one stops for 4 factorial, 3 factorial, 2 factorial, 1 factorial. Then when it hits 0, the 0 returns a 1, and that number will flow back. Okay, so let's take a look at a picture of that that's in the textbook. So let me stop share here, and let me share over here. Okay, so here's the idea. So if we have the factorial of 3, okay, so the number is equal to 3, and we look and we say that the number is not equal to 0, so therefore we're going to return 3 times factorial of 2. This stops. We then go to here. Okay, this is waiting. We're now here. The number is 2. Still not equal to 0. We return 2 times the factorial of 1. When we call this, this stops. We go down to this one. Okay, and it's still not equal to 0. We return 1 times the factorial of 0. This stops. We go to here. We now say the number is 0, and num is 0. We return 1. 1 goes back to the calling program and fills this in. So we now know that this is equal to 1 times 1. Okay, so this 1 times 1, or 1, is returned to here. We now know that the factorial of 1 is 1. So now we're returning 2 times 1. This will close down. It will send 2. So we now know that the fact 2 is replaced by a 2. I can't highlight the right thing, but you get the idea. By a 2. Okay, so then we get a 3 times 2, which returns a 6, which is the answer to the factorial of 3. Okay, so that's how factorials are going to work. So we can go back to the code here. So I'm a fan, aesthetically, I guess I would say, of the factorial. I think that it makes very elegant code. It's kind of cool the way it operates. It's going to lead to shorter code almost all the time, and often much simpler code, simpler to write. But, and I learned this long after I learned recursive programming, and it made me sad. But if you think about it, it makes sense. The problem with recursive algorithms is that they take up a lot of memory, because every time you go through a loop, so we just did 3 in the example there, we did 5 on here on our code. But what if we had 100? I mean, we would have all of these sections of memory being used. So it turns out it's not super efficient. And it's because of all that opening and closing and allocating and deallocating of memory, it's often not any faster either. In fact, it can be slower. So in general, if there's an iterative solution for a problem, that's a better way to go. even though I really like the idea of recursion. The problem also with recursion sometimes, it's not as clear, it can be more difficult to figure out. If somebody gives you a recursive function, then you may not know right away what's going on with it. Okay. So just to reiterate, a recursive function is one, I guess a layman's way to think of it is it's a function in C++ that calls itself. Okay, there's a little more to it than that, but so I guess the more official definition is it's a function that has a base case when it's done, but if not, it's going to call itself again with some smaller value. Okay, so that's the idea. So this is the last thing we're covering. In fact, when we get to data structures, we'll start back with classes and do a quick overview, hit pointers, and then go from there.